So let's talk about the Wheatstone Bridge lab. So in this lab, you're going to determine the resistance of an unknown resistor using a Wheatstone bridge. And we'll talk about that device and what it does here in a minute. Hey, lucky us, you didn't have to wait a minute to talk about the Wheatstone bridge because we're going to do it now. So this is the general schematic of the Wheatstone bridge. Has a battery, which if you remember, a battery supplies a potential, and there's an electric potential difference between the two sides of the battery. This would be something like 0 in our lab. This is going to be 2 volts. So electricity, electrons, are going to flow here. Some will go through R1, some will go through R2. They spend their energy as they go through these two charges. Now we know that voltage drops in parallel are the same, meaning if there's two paths. So if we have some electrons that go this way and up here, and then you have some other electrons that go this way and then reconvene, they all have to go through a change in potential of 2 volts because they start with 2 and they end back at 0. So parallel just means you can run through one without going to the other. There's this little meter that's stuck in the middle. That's your galvanometer right here. This is your galvanometer. This is the probe that you are going to be reading. Now, if this switch right here, if that switch is closed, if this potential drop is equal to this potential drop, there's no push on the charges through this bridge. However, if R1 is not equal to RA, then charge flows through V. So G is your galvanometer, reads current. Reads not 0. It reads current. If there's electrons flowing through here, that means that RA and R1 are not equal. Which means in this lab, you are looking for nothing. Nothing is a good thing. Now in our lab, we have a variation of this. We have what's called a slide wire Wheatstone bridge. And if you can think about it, this right here is a wire. If you go through more of the wire, it's harder to get through, which means it has a bigger resistance. Now, Ohm's law says that the voltage drop across a resistor is equal to the current flowing through that resistor times R, the resistance. As length goes up of this wire, as length goes up, R goes up. So by changing the length of this wire, where you put this little probe, it changes the resistance of that wire. In our lab, this is how it's set up. Your battery, right here, this battery, is equal to this voltage source. We'll talk about what to set that at. Your galvanometer is right here. We'll circle that in blue and red. And is attached to this little pin. So this little pin is right here. And your adjustable resistor is this resistor right here. And then your unknown resistor is going to put at Rx. So this is the one you're trying to find, right here in this little bridge. There are 2 little screws. You just unscrew them, pop it in. We'll talk about how to use our adjustable in a little bit. But I want to get back to the theory. How can we use this? How does it work? Previously we mentioned that the voltage drop, whether you take the top path or the bottom path, in this circuit is the same. That's because you start on the plus side of the battery and you end at the minus side. But we've also said that we want the current in this galvanometer to read 0, which means that the push through here, the voltage drop across Rx, must be equal to the voltage drop across RL, and the voltage drop across RA must be equal to the voltage drop across 100 minus L. If you think about this, this just says that Vx over RA is equal to V, I'm going to call this 1 and this side 2, V1 over V2. All this is saying is that I spend the same amount of energy comparatively in the top part compared to the bottom part per charge. So what that means is at this point in the circuit and this point in the circuit, the voltage, the potential, is the same. If it's the same, there's no push on charges through this galvanometer, and it reads 0, which is what I want. Next thing we have to know is if we use Ohm's law that says V is equal to the current voltage drop through an element is equal to the current through that element times the resistor. So we have this red current, so we have I red over I, and then times resistance, so this would be Rx, Ra, equals, we'll call this the blue side, which is equal to your blue current over, call this blue, blue, red, red, just so we have them marked, times R1 over R2. We will see that these i's cancel out, because if there's no way for current to get out of there, then it's going to be the same. If there's no current flowing through here, then any electron that goes in here also goes through that. Same thing here, none's flowing in here, so it has to go straight through. Now we know that if a wire is longer, it's harder to get through, so the resistance, how hard this wire is to get through, is proportional to length. We'll talk about resistivity later, but this is Rx over Ra is equal to L over 100 minus L. And algebraically, you will solve for Rx, your unknown resistor. All of this comes from the fact that you don't want any charge flowing through here, so the voltage drop in the top part of the circuit has to be the same in both cases, and the voltage drop in the bottom part of the circuit has to be the same. Otherwise, there would be an unbalanced push on electrons in the middle. So here's our power supply. This is going to supply the potential through the circuit. It's going to be like our battery. Make sure it's on the 6-volt setting because you don't want to fry anything, and you're going to set it for 2 volts. You can tell it's 2 volts because we're on the 6-volt setting, and we're reading this bottom scale that goes 0 to 6. So to get an idea of what your unknown resistor is, you can use the resistor codes, which are just printed on your resistor, and you can look them up here. Granted, resistors are only good to 10 or 15%, 5%, whatever. Not great for physics lab, but that's why you're going to measure it using a couple different ways, a multimeter and your Wheatstone Bridge. This box is your adjustable resistor. It is adjustable in the fact that whatever resistance you want, you just flip these little knobs. So what's the resistance set here? Well, the 30 knob is flipped and the 20 knob is flipped. So 30 plus 20, right now this is set at a value of 50 ohms. Ohm is just the... Now to use this, we know that Rx, Ra, the ratio of Rx to Ra is equal to the ratio of L to 100 minus L. What this means is that if Rx is a lot bigger than Ra, L is going to be bigger, and you'll balance farther down. If Ra is bigger, in this case, 100 minus L is bigger, and you'll be real close. You want to try to balance in the middle of the board. Close to it, try to balance in the middle. You're going to get the most accuracy and sensitivity in the middle. So that's why you will look this up using your resistor code. And then dial in something close. Then also remember that you want to do multiple trials, so at least 3 trials. And a trial would be a value of Ra. So 3 values of Ra and 3 times a piece. So for each one you'll get about 9 readings. Enough yammering, let's see what this thing looks like in action. So here we go, we take the probe and we touch it. And, whoa! Did you see that needle jump? That means that your bridge wasn't balanced and there's a lot of current going through there, which is not what you want. Whew, see, danger. And if you go the other way, oh, so a lot. So gradually keep moving closer. Oh look, and if you overshoot, it just goes the other way. So you're going to want to try to zero this down. And when you found it 0, record that as your L measurement. A couple notes just to recap on your data collection. If the galvanometer jumps quickly, remove the probe. Measure the balance point multiple times for different RAs. And then the balance point has to be somewhere between 30 and 70 centimeters. Otherwise, you're way off, and you want to have the most sensitivity you can, which is in the middle of your bridge. Because finding the resistance of one resistor just isn't fun, well, not enough fun as physics standards go, we've asked you to put them in series and parallel. So in series, you just put one resistor, then you take a clip the 2 resistors together, and you go through another resistor, R1, R2. Parallel means multiple paths, so you will clip the ends of the 2 resistors together, like that. And then you're going to measure the resistance from your Wheatstone Bridge using these unknown values. Again, if your needle goes too fine or you find you're not balancing in the middle, you need to adjust your adjustable resistor. The one with all those little switches. It's kind of fun to do. And it wouldn't be complete if we didn't talk about error analysis. So we have our resistor. There is error uncertainty of this given in your lab handout, so I would take a look at that. And then you have your length measurements. So you will know, oh look, multiplying and dividing, again you're just going to add percents to get your uncertainty on your R unknown values. Which brings us to the end. First note, be careful with the galvanometer. Measure the balance point multiple times with different values of RA. Use all the resistor combinations shown. There's a bunch there, so please walk through the lab report and go through them. Comment on what happens when the resistors are in series and parallel, and then make sure you compare to measured values. Well, I will see you in lab.